tertiary radical. So those would be the spots, right? And in either case, you'll be able to get the enantiomer for either one, right? Here and here, okay? So we're gonna get, if I draw all these out, okay, there's one, right? And we'd also get the enantiomer of that. So I'm gonna put plus En. Plus, we could get one here, right? And da-da-da-da. And plus En, right? Just like that. Hopefully, again, that makes sense. If not, I guess you can email me. Let's look at one more thing from chapter 11, then I think that'll be it. We're going to look at allylic halogenation. So we'll get the allylic position, right? We have a double bond, and we'll get the allylic position, removing a hydrogen from there, creating a free radical, an allylic free radical. Okay, carbon double bonds affect regioselectivity. Mainly because we're going to see that sometimes our resonance, we can form a resonance structure, right? And then it can react with the resonance structure or the original structure. That's not going to come up in our original example. It's going to come up in an example I'll show you at the end. Anyway, let's go back here first. Let's get back here. Getting ahead of myself. So carbon double bonds affect regioselectivity sometimes, okay? Let's take a look at this thing here. Let's take a look at the delta H value to extract each one of these protons. Let me grab some more chalk. This one, 440 kilojoules per mole. That's why it doesn't react there to break that bond. This one, to break this bond, is 364 kilojoules per mole, and this one is 402. Now, why would this one be lower than that one? Again, I know you're thinking ahead, and you're thinking, boy, Cliff, it's probably because there's resonance structures, and you are correct. When we take this off, right, from here, we'll have a resonance structure, which let me draw that. Actually, do I want to put that on there? I'll just draw it this way. Say we remove this hydrogen right here, okay? And we end up with this, right? You abstracted that hydrogen, right? Well, we have one resonance structure anyway. And we'll end up with this. Now note, for this particular molecule, Whether or not you added a bromine here or you added a bromine here, what's it gonna be? They're gonna be the same, right? Be the same. You'd end up with a stereochemical center recent mixture, but my point is, you can flip this over, right? If I take this molecule and I rotate it and flip it over, these two are the same. So in this particular case, it's not gonna make a difference that we have resonance structures. But in other cases it will, which I'll show you. Anyhow, so we have resonance structures. So this is resonance stabilized if you chop off that hydrogen. Long story short, okay? So let me draw this here real quick. Let's finish this example. And we ended up with something like this. Okay, that's what you're gonna end up with. Again, even if you moved your free radical over here, your double bond would move there, you'd end up with the same product, okay? So the resonance structure doesn't matter for this one. All right, I hope that I explained that so it all makes sense, hopefully. Now, some of you might have been wondering, or maybe not, before when we had Br2 and we had CO2 or whatever, and we had a double bond, what did we have? We had anti-addition across the double bond, right? So that would happen here. That would be a competing reaction. So what do we do so we don't have the competing addition reaction? Well, we use something called NBS, okay? N-bromosuccinimide is what we use, okay? To avoid the competing addition reaction, we use NBS. And I will draw this bad boy out here. Right, again, remember, when we had a double bond, we had Br2 or CO2, what do we have? We had an addition reaction. You added anti, it would be anti on this ring, right? One on each side. Anyway, so to avoid that, we're going to use NBS. And here is NBS. And so we get a bromine radical from this by smashing this thing with some UV light, some electromagnetic radiation, H-nu, right? And we end up with, this will be stabilized by resonance. Plus a bromine radical, like that. And then this is stabilized by resonance. Sorry, this chalkboard's messy. Hard to see my electrons, right? I could draw a resonance structure for this wall, shit, right? I could go like this. Like that, right? Draw a resonance structure, there'd be another resonance structure down there. Anyway, long story short, that's resonance stabilized, right? And now you got your bromine that you can use in a reaction to brominate an alkane, right? And let's see here. So let's take a look at an example. Allylic halogenation with NBS. All right. So what products are we going to get with this bad boy? Well, there's a tertiary, right, hydrogen there, right? If I abstract that proton, what am I going to get? I'm going to get a tertiary free radical. So that would be the most stable, right? That would be the most major product. And actually, right, you'd have it in the enantiomer. Okay, right? Again, it's not stereospecific. I guess I can draw that in there. I'll just draw it in there and make it But now, what happened when we subtracted this proton from here? Right, what happened? You had a free radical here. Could we have a resonance structure? Yes, you could, right? Half arrow here, half arrow here. Your double bond would be there, half arrow there. So you have a free radical here that could join up with the bromine. So we're going to end up with the bromine on the end. Like so. Again, let me draw that out real quick. Let me draw it. Here's after your hydrogen abstraction, right? Bromine abstracted a hydrogen proton, right? And your free radicals there. So because of resonance structures, we'd end up with three products, right? Again, this thing is not stereospecific, so you end up with the racemic mixture, and then you end up with this other product because the free radical has a resonance structure. All right? Yay! Okay, that's it for chapter 11.